That's the only, or one of the very, very few papers that where actually the authors had an actual chip that implements cognitive radio, where they had a transmitter, receiver, and sensing radio. So we just borrowed the figures, the numbers from them, and used them to calculate the power. Regarding the results, first I'll talk about the throughput and collisions as a function of the number of stages, number of sensing stages. This figure is for slow primary user traffic, fast primary user traffic, and the blue line is throughput, the red line are collisions.
So for modeling the traffic, is that based on someone's measurements or the?
Yes, we refer to actually papers that with empirical results regarding traffic. So the blue line here is for throughput, the red line is for collisions. And we looked at two cases, one where the sensing time is short, so the probability of false alarm in midsection is high, and vice versa. As you can see, multi-stage sensing, as you increase the number of stages, multi-stage sensing increases the throughput. Okay? The case with only one stage usually results in lower throughput. The other observation is the optimal number of sensing stages is a function of the sensing time you have and the primary user traffic. The other interesting observation is the collision increases with number of sensing stages. This is because obviously the second user stays in the channel for longer time. Regarding the energy consumption, here the red line accounts for the transmitting and receiving power, or actually it's the energy per bit, and the blue line accounts for the sensing energy per bit. As you can see, the increasing number of sensing stages decreasing your energy per bit. Finally, we want to look at the relationship between throughput energy, and at the x-axis you have the sensing time. Here the case is if your sensing time is too short, you have too much false alarm detection. If it's too long, you don't have much throughput. So these lines are for different numbers of sensing stages, 1, 2, 3, 4. And as you can see, for each number of sensing stages, there's an optimal value of sensing time that maximizes your throughput, and another optimal value of sensing time that minimizes your energy per bit. So the takeaway from these figures are you have to do joint optimization of sensing time and number of sensing stages in order to maximize throughput, minimize energy, and minimize collisions. So this concludes the first part of the talk. So we showed that multi-stage sensing is beneficial. You increase your throughput, you decrease your energy per bit spent on sensing. The main drawback is you get higher collisions. And the multi-stage sensing, what it does, it increases your degrees of freedom, which helps you in reaching a better compromise between these methods. Now I'll proceed to the second part of the talk, which is for the same algorithm, what would you gain if you put the traffic information of the primary user into account?
So just a quick question. So you had the analytical in your last set of charts, you had analytical results, and then you had simulations. So how do you do the simulations? Is this done in?
It's MATLAB Monte Carlo simulation.
Okay.
Yeah.
Oh, MATLAB.
So the second part of the talk is how knowledge of primary user traffic would impact your performance. And we have a paper in progress working on it. And so what I did is I modified the multi-stage sensing algorithm so that you account for the different primary user traffic statistics. So basically this part is, again, the multi-stage sensing algorithm. The only difference is when you leave the channel, at first we assume that you have knowledge of the duty cycle of the primary users. When you leave the channel, you go to a channel with the minimum duty cycle. In this part of the work, we assumed that the primary user and the second user are not synchronized anymore. I know that that was an assumption we did in part one. It's a typical assumption in literature, but we thought by doing this, of course, the math would be much harder, but we would target a more general problem. So now I'll talk about how the analysis is done. So basically, at first, you generate a number of channels with different duty cycles, and you calculate an estimate of the duty cycle. We showed a case where these estimates are accurate, and with this, these estimates have an error in them. You sort these channels, and then using a discrete time Markov chain, we calculate the stationary probabilities of the second user being in a transmission or a sensing state. And then using a continuous time Markov chain, we calculate the metrics, that is throughput and collisions. And I will explain this part now. So as I said, we have an assumption, we dropped the assumption that primary user and secondary users are synchronized. So now the process is much more stochastic. So consider this case, the second user starts transmitting on a channel for a period of time, t, and this is the traffic of the primary user on that respective channel. The primary user would appear and leave the channel at random times. In this case, so in the previous part, we used the Gilbert-Elliott model, which basically had geometric distribution. So the continuous time analog for that is the exponential distribution. So here we're assuming that the on and off times are exponentially distributed. And we use the continuous time Markov chain model to calculate the throughput and collisions. And these are the expressions. Basically, this is the expected throughput if the second user starts transmitting with the primary user is idle or active. And these are the expressions for the throughput and for the collisions. And these lambdas, they account for, these are parts of the exponential distribution that I will discuss in the next part of the presentation. Regarding the results that we got here, x-axis is number of channels, and the solid lines, throughput, the dashed lines are collisions. The black line here, this is the case with multi-stage sensing with no knowledge or doesn't put into account the primary user traffic into consideration. The red line puts into consideration the traffic of the primary user and assumes that traffic is perfectly known. And the green and blue are, there's an error in the estimation of the primary user traffic. Here in the green line, we assume that you use only 5 samples in estimating the primary user traffic. In the blue line, 50 samples. So obviously the error in estimating the use is less, and hence the throughput is higher. So as you can see, putting into consideration primary user traffic, you end up with higher throughput and lower collisions. And also another observation here is obviously error in estimating the primary user channel would limit your benefit. So
you just estimate offline, or while you're doing your attempts to transmit?
So we assume that the second user tries to estimate these parameters before, at the very beginning.
Offline.
So offline, yeah. But it can be done online as well. I mean, you can keep on you can keep on trying to estimate the traffic. You can keep on trying to estimate your traffic, and by that you would improve the accuracy of your estimate. Here I'm showing the relationship between the root mean square error in estimating the duty cycle and the throughput. The throughput here is the blue line. Obviously, throughput will decrease. And the red line here accounts for, as I said at the very beginning, what you do is you sort your channels in an ascending order of use. So this is the probability of getting these channels in the correct order. So again, what you conclude from this figure is, yes, increasing error decreases your throughput. And this is the concluding part of this part of the talk. Yes, primary user traffic knowledge of it would increase, throughput decrease collisions, and error would limit this increase.
You assume that the primary uses the same characteristics?
For the different channels?
No matter, it depends on the channel or independent of the channel? Or it doesn't matter?
So we generate a number of channels for the primary use, different channels, and the duty cycle is uniformly distributed from 0 to 1.
But even if it was different, so you know the using on channel 1 is a particular TV channel with this particular characteristic, channel 2 is a different you would be able to handle also non-uniform, right?
So what do you mean by non-uniform? Oh, non-uniform distribution for you?
For the parameter of the parameter.
Yeah.
He assumes they are different. Every channel has a different.
Oh, okay, so you assume they're
That's what you
different
mean.
per channel.
Uniform means like a random number.
Or uniform
from
within a
uniform.
channel, but
Yeah.
it changes from channel to channel. Okay.
Yeah, yeah.
That's
I mean,
fine, that's fine.
like to select the duty cycle for a channel, you choose a random number between
Right,
zero.
right.
So the next part of the talk, we look at the part where, so as from my previous figure, I showed that increasing the increase in the error in estimating your duty cycle decreases the achieved throughput. So the next slide, the next part of the talk, I'll talk about how accurately can you estimate primary user traffic. So this part of the talk, this part of the research, it got accepted with minor revision at JSAC. Hopefully it will get accepted eventually, otherwise. Anyway, so the problem here is you are trying to estimate the primary user traffic, and you do this by sampling your channel. So assume that you have sample stream Z, and the second user tries to estimate the traffic parameters. And obviously there should be an error in the sample stream because the sensing process is imperfect. You have probability full SORAR misdetection. So basically the problem statement is you have n samples and with intersample times that are vector tau, and you want to quantify the error in estimating your T off, T on, and the duty cycle. T off is the average off time, T on average on time, and you want to estimate the duty cycle, the error in the duty cycle as well. And again, we do the assumption that T off and T on are exponentially distributed. This is a look at the traffic model. So as I said, the on time and off time are exponentially distributed. This is the exponential distribution, and the average off time is given by 1 over lambda f and 1 over lambda n for the average on time, where lambda is the rate parameter for an exponential distribution. U is calculated by lambda f over lambda f plus lambda n. And for the coming derivations, we'll need a lot of these expressions, which are the transition probabilities. So in this case, primary user is assumed to be continuous time process, so we use a continuous time Markov chain. Oh, sorry, continuous time Markov chain to calculate the transition probabilities from idle to busy, idle to idle, busy to busy, and so on in a period of time t. These expressions were derived by Tang Shen in his work in transactions on mobile computing.
So what types of traffic are empirically approximately exponential?
So their empirical results, they show that GSM and traffic in the ISM bands, they either follow exponential distribution or log normal. So these are typical traffic scenarios.
But if you were worried about more fixed things like TV stations and whatever else, this goes away, right?
Yeah, because TV stations would be there for days.
They're there the whole day.
Yeah. This is for more dynamic traffic.
Yeah, I was thinking like even if you don't want to have this strict like primary license, like, even if you want to be like a good citizen in a channel, you would do something like this to minimize the collisions,
right? Except you worry less about the collisions.
Yeah, but I mean, we have the framework to optimize the collisions,
exactly. Right?
So that so it's more like coexistence rather than strictly going by
Right, yeah. Okay. More useful.
Stop you for a moment. Let me ask you, so you make the assumption there is just a pair of secondary users?
There was, sorry?
One pair of secondary users
Yeah.
trying to compete for free channels. What if you have a pool of pairs?
No, actually, the pair of secondary users, one is transmitting to the other one. They're not competing, they're collaborating.
No, but
yeah.
each pair is, but suppose now I've got 2 pairs doing the same game, or 3 pairs. In fact, there will be n pairs trying to get in.
What would happen is people usually, I mean, this is studied in literature under the name collaborative sensing. So in this work, we assume that the probability of full surround probabilities